Hello, class. Gonna wait for a few more to join up. Oh, we're over 20. Okay. So this should be a fairly quick lesson today. Because I split the lesson in two because of the midterm. If you can't see, I'm tired today. I have bags under my eyes. Hazel has been, my dog Hazel has been sick, and so there's a lot of cleanup. So I'm kind of, I woke up in the middle of the night last night and I had to clean up some stuff. So it was not very fun. Last time we talked about torque. So let me just do a review of last time. Torque was a twisting force. It's denoted by the Greek letter tau. And torque is equal to R times F perp. All right? Where the picture you want to have in your head is you have some blob. And the blob has a pivot point. And there's some location on the blob, for example, maybe right here, where a force is being applied. We draw a line from the pivot to where the force is applied. And the length of that, or a line segment, I should say, the length of that line segment is called R. And then once we've drawn that line segment, we look at the force vector. Remember, vector is just another fancy word for arrow. And we look at the component of the force vector that is perpendicular to that line that you drew. Okay. So you would have to use trigonometry. You might figure out what this angle is and do a cosine, or you could find out what this angle is and do a sine. And you get the perpendicular component. So that's for a single force. Of course, we have the idea of net force, or net torque, which is just the sum of the individual torques. Okay. If a torque would create a counterclockwise rotation, then that is a positive torque. And if it would tend to create a clockwise rotation, then that is a negative torque. So go ahead and type it into the chat if you know whether this is a positive torque or a negative torque that's created by this force. Okay. In particular, if the net torque is 0, then that will imply that there is no rotation happening. All right, so that was basically the content of the last lesson. That is correct. This would be a negative torque. So the way you determine that is, like I can just use my imagination and I can just think about which way it's going to rotate. But if you're having trouble seeing that within your mind, just grab anything that's near you, put your finger down to make the pivot point, and apply a force on the object. So I can see that I'm applying a force kind of like up here, and it goes up and to the right. If I apply a force at that location, I can see this thing is rotating in the clockwise sense. Okay? All right, so we're going to talk about basically 3 concepts today. The first concept is called center of mass. Okay, and all right, and so we're actually going to come back to center of mass later on in this unit on another day, but today I just want to briefly introduce what center of mass is because we need it for the next topic that I'm going to talk about. So center of mass is typically denoted by XCM for center of mass. And you could think about it as the average location of the mass within an object. Okay, average location of mass within an object. Typically, if you have a blob, for example, the symbol for center of mass is like the BMW sign. So that if I drew something like this, that would mean that the center of mass is at that location. That's kind of the engineering notation for center of mass. Now, if you have what often is the case is you have a uniform object. Okay, so let's say I had a uniform rod, for example. So when I say a uniform rod, I mean that the rod has a constant density throughout. Okay. So I'll just say uniform rod. If you have something that is uniform, then the center of mass is going to correspond with the geometrical center of the object. Okay, so because this is a uniform rod, the center of mass is going to be in the geometrical center. So the center of mass might not be the geometrical center of the object. Okay. So it might be something like this. All right. However, if you have a non-uniform rod, okay, so let's say you had a rod, for example, where there's more mass on one side than another side. Okay, so maybe I'll try to draw that here. Something like that. See how I'm trying to represent this as like a gradation in the amount of mass. So there's more mass on this side. If there's more mass on one side, then that's going to shift the center of mass towards that side. Okay, so maybe the center of mass is right here now because of that. Okay, we're not going to worry about how to actually calculate center of mass until that lesson that I said is coming. So today we're only going to deal with uniform objects. So the center of mass is actually the center. Okay. All right. So another way you can think about the center of mass is it is the balance point. So if you hold something by its center of mass, it will balance. Okay, so I have one of my knives right here. All right. So if I look at the profile of this knife, I can see that there's a lot more metal on this side than there is on that side. Now this is a what's called a full tang knife, so it has metal going all the way through, but there's a lot more metal on the blade side than there is on the handle side. So that would tend to indicate that the center of mass might be a little bit towards the blade end. But also you have the fact that it is thicker here. So that so what I can do to find the center of mass is I can just try to balance it. Okay, so here's the geometrical center, and I can see that I can't balance it. It wants to swing to this side. So I'm going to move my finger more to the other side. So the center of mass is about right here. Okay, see that? It's balancing. So it's almost in the geometrical center. All right. Let's see if that's true for some other ones. So here, this knife is a lot thinner, so I'm thinking that it's going to be more to this side. Oh, but it's not. Okay. So anyways, that's one way you can find the center of mass, just by trying to balance it and seeing where you have to hold it to make it balance. Okay. So the next thing I wanted to talk about is what's called the gravitational torque. So that's very simple. It is the torque caused by the gravitational force. All right. So yeah, like for example, if I'm holding this calculator and I put the pivot point over here, see how it swings? It rotates automatically. The reason it's rotating automatically is because gravity is exerting a torque which is pulling this thing down. Okay? So that's called the gravitational torque. Okay? So what I want to imagine is let's say we have a rod. Okay? The rod is uniform. It has mass m and length L. Okay. So because it's a uniform rod, the center of mass is going to be in the middle. Okay. And we'll put the pivot point on the left end. Okay. So the question is, so gravity is pulling down on every part of the rod. The gravity is pulling on this piece of the rod right here. Gravity's pulling on that piece of the rod. Gravity's pulling on that piece of the rod. That piece of the rod. It's pulling down on every single part of the rod. Okay. So that means it's a little bit complicated because we got to figure out what's the torque on that part, plus 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 the torque on that part, blah, blah, blah. So how do we calculate? So there's a simpler way to calculate the gravitational torque if you know where the center of mass is. Okay? And it turns out when calculating gravitational torque, you can treat the weight force as if it were concentrated at the center of mass. Okay? So I can treat it as if all of the weight force mg were just acting right at that location. So basically, remember how when you're calculating torque, where the force is applied matters. Okay? And so when you're calculating the gravitational torque, which is the torque due to the weight force, hang on one second. When you calculate the gravitational torque, which is the torque due to the weight force, you can draw the weight force arrow as being located at the center of mass. Okay? So let's say that I wanted to calculate the gravitational torque in this case. All right? The torque is going to be R times F perp. So where is... So I'm going to box this in because this is the main result. So what is the R value? What is the distance between the pivot point and where the gravitational torque is acting from? Well, because this is a uniform object, the center of mass is in the center, which is going to be L over 2 from the pivot point. Okay? So we have L over 2 is going to be our distance. And then this is the force is the weight force. So my force is going to be mg. And it is already perpendicular in this case. All right? See how the line connecting the pivot to where the force is applied is horizontal, and the weight force is vertical. Okay, so it's already perpendicular, so no trigonometry is needed in this case. Now this explains why the center of mass is the balance point. Because what if the pivot point coincides with the center of mass? So, in other words, what if pivot equals the center of mass? Okay. In that case, here's the center of mass. Here's the pivot also. So what is the R value that we would use in that case? I'll wait for someone to type it into the chat. What is the R value that we would use if the pivot and the center of mass coincide with each other? Somebody, anyone, please. Okay, no one wants to answer. So remember, R represents the distance between the pivot and where the force is applied. So if the force is applied at the same location as the pivot, then R equals 0, which means that the gravitational torque is 0, which means no rotation. Okay? So that's why if you hold something from the center of mass, it does not rotate. So that's how you can locate the center of mass, is you just try and pinch it at a point where it doesn't rotate. So this is the center of mass. See how no matter what orientation I hold it in, it doesn't want to rotate because it's balanced. Okay? If I hold it from a different location, there's a separation between the center of mass and the pivot point, so it has an R value. Okay? Another interesting thing is you might notice that if I hold something by a location that's not its center of mass, it'll swing like this, and then it'll stay put. And basically what's happening is if you have an object, so let's say I have a rod right here, and it's pivoting. So the gravitational force is acting straight down. So here, the gravitational force is perpendicular to the rod. So it's going to start to rotate. So maybe it rotates down to this location. Okay. When the rod is in this location, we can see that the gravitational force isn't quite as perpendicular to the rod anymore. So that means that the torque due to gravity gets smaller. Okay? And what happens when the rod is vertical? Well, in this case, the gravitational force is actually parallel to the rod. So that means that F perp is 0. Okay? So what happens is gravity will swing something until the weight force is parallel to R. And so what that means is that an object will swing until its center of mass is directly below the pivot point. All right? So if I hold it like this, I know that the center of mass is directly below where I'm holding it. Okay? If I hold it from a different if I hold it from a different location and let it swing, then the center of mass is directly below that point. Okay? So, kind of a neat thing. All right. So now we get to the thing that I really wanted to talk about today, which is something called static equilibrium. Okay? Static equilibrium. So, static equilibrium. All right. So, static equilibrium means that an object is not translating and not rotating. Okay? So what is a translation? A translation means that it's moving from place to place. Okay? So these would be examples of translations. Okay? Rotations means that the orientation is changing while it stays in place. So this is a rotation. This is a translation. You can have one or both, okay? So to be translating without rotating is this. To be rotating without translating is this. To be translating and rotating is something like this, okay? So if it's not translating and it's not rotating, it's just completely still. So that's why it's called static equilibrium. So not translating means that the net force on the object is equal to 0. Okay, if the net force is not 0, it will start to accelerate, okay, from its original location. Okay, not rotating means that the net torque is 0. Okay? So if you have both of these things true, then you will have static equilibrium and the object will be completely still. All right? So this is used in engineering a lot. Any physical structure that you want to be completely still, must have a net force of 0 and a net torque of 0. All right. So that's used to figure out what the various forces and torques are within the object. So these are the conditions for static equilibrium. All right. And these are the conditions for static equilibrium. And because these are two equations, we're going to get a system of equations when we solve this. Okay, so let me show you how this works. Oh, by the way, for static equilibrium questions, you can choose the pivot point to be wherever you want. Because if you think about what is the pivot point, if an object is rotating, the pivot point is the point where it's not moving. Okay? Every other part of the object is moving but the pivot point. It's held fixed. If you have static equilibrium, then the entire object is not moving. So every point is the pivot point. So you get to choose where you want the pivot point to be. All right? So for static equilibrium questions, you choose where the pivot point is. Okay? So let's do an example. Let's suppose you have a uniform rod of mass let's say 5 kilograms is support and length 10 meters is supported by 2 ropes. One rope is at the right end. Okay. The other rope is 1 meter. Actually, let's say 2 meters from the left end. Calculate the tension in each rope. Okay. So if I were to draw a picture of this, all right, here's the rod. Because it's a uniform rod, the center of mass is in the middle. Okay. And the size of the gravitational force is going to be 5 times 10, 50 newtons. Okay. It has a tension pulling up on the right end. So I'll call that T sub R for right end. Okay. And then 2 meters from the left end. So this is 2 meters. All right. There is a torque or a tension from the left rope. Okay. So we want to figure out what are these two tensions. Okay. So how are we going to do that? We're going to apply static equilibrium because this rod is just sitting horizontally. Okay. First of all, I'll apply that the net force is 0. And when I say the net force is 0, I mean the net force in the y direction is 0 in this case because there are no horizontal forces. Okay? So the net force in the y direction equals 0. And there are 2 up forces and 1 down force. So TL plus TR are the 2 up forces, and the down force is 50. All right. Okay. So that is our first equation. All right. The net torque also has to be 0. Okay. Now, what I want you to notice, so I'm going to choose the pivot point to be right here. So I choose the pivot to be there. All right. Now, my advice to you is always choose the pivot point to be at the location of one of the forces. It doesn't matter which one it is, but at the location of one of the forces. Because if you choose the pivot point to be 0 at the location of one of the forces, then that force doesn't have a torque because it would have an R of 0. Okay? So, if I choose this to be my pivot point, then I have 3 torques to add up. Okay? The first torque is the torque due to T sub L, but it has, so remember the formula for torque is R times F per, okay? So because this force is acting at the pivot, it has an R of 0. So we get 0 times T sub L, okay? So that's nice. Now we look at the torque due to gravity. And if I'm taking that to be the pivot, I can see that gravity is trying to swing this rod in the clockwise sense. So gravity is going to have a negative torque. Okay? How far is gravity acting from this pivot point? Type it into the chat if you know how far gravity is acting from the pivot point. Keeping in mind that it's a 10-meter rod. I'm going to wait for this person to figure out their car. They're having a really hard time. Oh my gosh. Three, excellent. So because the center of mass is going to be the middle of the rod, it's 5 meters from the left end, and we already have 2 meters over right here where the pivot point is, so the extra distance is 3 meters. Okay, so while I'm typing that, or while I'm writing that down, someone tell me what the R value is going to be for the right tension. Okay, so for the gravitational torque, its distance from the pivot is 3 meters, and its force value is 50. Because the rod is horizontal, the gravitational force is perpendicular to that line, so I don't have to do trigonometry. Okay, so lastly, I have the torque due to the right rope. Okay, and I can see if this is the pivot point, the right rope is pulling up, which is going to tend to rotate the rod in the counterclockwise sense. So that is going to be a positive torque. And as I see in the chat, the correct answer is 8 meters. This force is acting 8 meters from the pivot because the total length is 10 and the pivot is 2 meters away from the left end. So the extra length is 8 meters. And then the force is unknown, so I just put T sub R. Okay. All right. and it's already perpendicular, so I don't need to mess around with trigonometry. So this is my second equation. So this is a system of equations for two unknowns, left tension and right tension. But it's a very simple system of equations, all right? So I would get 0 equal, so if I rewrite this equation, I have 0 equals 0 minus 150 plus 8 t sub r. All right, and so I can solve that very easily. It says t sub r equals 150 over 8. I kind of want to scream shut up out the window. I've never done that before. So that says that the tension in the right rope is 18.75 newtons. Shut up! I'm not really angry about it. I just wanted to yell shut up. So now what I'm going to do is plug that into my first equation. So now I have 0 equals TL plus 18.75 minus 50. And that's a very simple equation to solve. So that says that the left tension is 31.25 newtons. Okay? So there you go. That's an example of a static equilibrium problem. Now what you're going to find is that whichever rope is acting closer to the center of mass is going to carry more of the weight. Okay? So notice how the left rope is closer to the center of mass than the right rope, so it's going to have more tension in it. Okay? So that's just something to think about. I'm not going to do another example, but I just want to talk about a question in the homework. Sometimes the center of mass is unknown at an unknown location. Okay? So what if you didn't know where the center of mass was? So for example, what if you had, a 50 Newton force going up right here, and you had a, let's say, 30 Newton force going up here, okay? And you don't know where the center of mass is, okay? So I'm going to take my pivot to be right there, so that this 50 Newton force exerts no torque. Now, because the total amount of upward force is 80 newtons, that means that the weight must be 80 newtons, right? Because the up forces have to match the down forces. But we don't know where the center of mass is. So let's just give it a variable. Let's say it's x, a distance x from the pivot point. All right? Then setting the net torque equal to 0, setting the net torque equal to 0, we get 0 torque from the 50 Newton force. We get minus 80x from the gravitational torque. And I didn't give the total length. So let's say the total length is 2 meters all the way across. And then we have plus 2 times 30 for the other torque. So see how using this equation we can solve for the location of the center of mass. So this is actually one of the ways that you, one of the ways that the location of the center of mass is calculated in practice. If you didn't know where it was, you just sort of hang it from 2 scales and you compare the weight readings on each scale. Okay? So that's my lesson for today.